Hello and welcome back. Today we are discussing section 2.1, the derivative. We are tackling really all of the second learning objective and trying to cover part of the third one, just so the final video for this section isn't 16 hours long. It's an exaggeration, but still. So we'll define the derivative, we'll study its basic properties, and then we're going to try out an example. So the previous video had finished with essentially computing the average rate of change on a tiny, tiny interval. And just to remind you of some of that terminology we were using, the tangent line was what we imagined this slope to be, the slope of a line that perfectly touches this graph right along its edge and has its slope equal to what we get when we take 2 points on the curve and make them closer and closer together. So the derivative is actually really the primary tool we're going to be using this term. We'll study it first just for its nature, and then we'll apply it in a few contexts where it makes itself pretty useful. So the notation for this we can get used to, but this apostrophe is supposed to denote the derivative of some function. So we start with f, and then if we write f with a little apostrophe, this is usually read f prime. So f prime of x is, and here we see the limit as predicted. So we're basically just saying that if we look at the limit as the 2 points get closer and closer together, our interpretation of h is how far away from x we are. So if we start at some point x, we go up or down just a tiny little bit, we're trying to imagine what happens as that distance gets smaller and smaller. And so this really is supposed to remind us, the same way that average rate of change should remind us, that what we're looking at is essentially just a difference in slopes. So the slope of this function looks like difference in outputs on top, and h doesn't look exactly like a difference in inputs, but it actually is. If we look at the inputs on top, x plus h is our initial input, and then we're supposed to subtract this other one. So if we do that, x plus h minus x, the x's disappear. So this h on the bottom really actually is x2 minus x1, if you will, from the slope formula. So this is a very fancy version of slope, and it's as the 2 points that we use to calculate it get closer and closer. And then to reiterate this definition of tangent line, if we pick some point on the graph c, f prime of c is supposed to be the slope of that tangent line. And then one final piece of terminology just to make the verb out of derivative. So derivative is a noun. I would find a derivative, compute a derivative, and that process is called differentiating. So I would differentiate f. That's the same as find the derivative of f. So one brief example just to get us in the ballpark, we'll reuse our linear function from our average rate of change calculation earlier, and we'll say, look, here's the definition of the derivative. So this is just taking exactly what we've been told in that previous definition and putting it on the page. Then with some simplification, well, it doesn't look much simpler for sure, but with some expansion, I suppose, we could take this expression, and all this corresponds to is f of x plus h. And the way we expand that, as usual, when we evaluate a function is to go back to the original defining function, 3 minus 2x in this case, and replace all the x's with x plus h. So instead of 3 minus 2x, we've got 3 minus 2x plus h. Then we still got one other computation to do. It's not quite as bad because it's just rewriting the function again with x as the input. So down here we've got 3 minus x back again. 3 minus 2x, yeah, our original function. And from there, we can do some algebraic simplification. And, you know, we're supposed to be thinking about, I sort of imagine that this limit is sort of like a tether holding a really excited dog. At any given moment, what I'd really like to be doing is plugging in 0 for h. But if you notice, if we plug in 0 for h, this is going to cause us to divide by 0. So I can't use that great theorem about limits that just lets me plug this thing in. And now, my hope, since I can't do that at the moment, the hope is that these things on top will simplify and combine, cancel, something interesting will happen, such that we get rid of the h's. So if we do some expansion, all that happened here was that we multiplied the negative 2 through, and then we distributed this negative sign. So it was negative 2x, which makes plus 2x. But now you can also see that there's some cancellation that can happen here. You have 3 and minus 3. We have negative 2x and positive 2x. All that leaves us with is negative 2h on top and h on bottom. But those cancel as well. So our h's are actually out of the mix. And I'm constantly searching for this moment where I can let the dog off the leash, as it were, and actually just plug in 0 for h. And finally, that moment comes, but although for this particular function, this particular limit, it's not terribly exciting. We have the limit of a constant, and one of our helpful limits from way back in the day says that if you want the limit of a constant, it doesn't even matter where this is going because there's no variables here. The limit of the constant is just the constant back again. Now, just for perspective, this shouldn't be a surprise to us because the slope that we computed, the average rate of change we computed earlier on in the previous video for this function, 3 minus 2x, is the exact same computation. We arrived at the exact same answer. And that's because we have a line, and a line has a constant rate of change. So just like the average rate of change we figured out earlier, this derivative, or what we'll call an instantaneous rate of change, like in an instant at a particular point, not just between two spots, the instantaneous rate of change is also just the slope of this line. Any point we pick on it is going to have a slope of negative 2. Okay, so we're going to try out an applied example to give this some context. So cost in dollars to produce K quarts of kettle corn. We saw this when we did our average rate of change computation earlier in the previous video. So our job is to compute the derivative of the cost function and then answer this question. Instantaneous costs, so this instantaneous rate of change thing is a piece of new terminology. This just means the derivative. So I could even write these are equal to one another. So at what instantaneous rate is cost changing? When 10 quarts are produced. So we're going to find some instantaneous rate thing, and then we're going to figure out what it looks like at, I think, k equals 10, since k is how many quarts we produce. So we can figure out the derivative. We start with our limit the same way. I guess cosmetically this is different because instead of f of x, it looks like c of k. But other than that, it's the same deal. C prime is this limit as the slope fraction has the points go closer and closer together. So you'll have to sort of steel yourself for some algebra here because boom. But this is really just taking the same structure that we had before. This whole piece, though, since our cost function was a little more complicated, this whole piece is c of k plus h. And then our other function, well, just the function back again, no changes in input, is this second set in parentheses. So what we have is this kind of algebraic monstrosity, and all the while this limit is hanging out, waiting here until we actually have an opportunity to use our nice theorem and quote, plug in h. It's not really that, but the theorem says that the limit is equivalent to what we get when we just plug h in. So we're just waiting for a chance to plug in 0 for h when this thing is undefined. So we've got some expansion here. So here's all the algebra from expanding that last term. Again, be careful with the squared piece. We have to do that FOIL if you'd like, or make sure at any rate that our quadratic term got multiplied by itself. And this actually has a little bit of good news for us, though, because there's a variety of things that are like terms in this. We've got positive 0.01 k squared, negative 0.01 k squared. Let's see what else. We've got a 0.5 k and a minus 0.5 k. We've got a 50 and a minus 50. That's all really helpful because now our expression looks like this. We went from 9 terms down to 6 terms. That's got to be an improvement. But still, we can't really plug in 0 for h. It would still cause us to divide by 0, so we're kind of biding our time here, hoping that algebra saves us. Yeah, that sounds like a great idea, right? Wait for algebra to save you. And yet, it actually does work out here pretty nicely, because if you notice, this has a factor of h, this has 2 factors of h, this has a factor of h, and so does the denominator. So we can actually cancel a factor of h out of every one of our terms, and that's because h is multiplied to the top at least once and to the bottom at least once. And that leaves us with no h's on bottom. And this is the moment of truth, basically. This is the point where we can say, look, there's no reason why h equals 0 would be undefined here. There is no division anymore. So here's where we say, look, our nice theorem back from section 1.5 tells us that this limit is the same as what we get if we just dumped in 0 for h. So limit goes away at the same time we kind of pull the trigger on that and say, look, this is the same thing as h equals 0. So that whole term disappears. Negative 0.01 times 0. And then we're left with these other two terms. So this right here is a derivative function. It is a machine that we give it an amount of kettle corn and it spits out how quickly cost is changing. Not just what is the cost, but how quickly cost is changing. So it relates to cost in that fashion. So we say c prime of k equals this stuff, negative 0.02 k plus 0.5. But remember, our task wasn't just to find the formula for the derivative. What we wanted to know was the instantaneous rate of change when we're producing 10 quarts. In that split second, we take a picture right when we've produced 10 quarts. How quickly is our cost function changing? But that just means we take our derivative function and plug in 10 for our input variable. So c prime of 10, all right, replace k with 10. A little bit of simplification later. And this is a fine answer, but it turns out the next statement was one of the most important pieces that we've got going for us, and that is the statement in context. So I'm not claiming that there's something perfect about this, but it definitely is an important thing to get used to writing statements that make conclusions about derivatives, because calculus is the study of the rates of change. So this gets a bunch of exclamation points because this is one of the things that I guarantee you I will ask you to do on an exam, and probably on all of the exams in different ways. So interpreting our conclusion is extremely important for this course. So when producing 10 quarts of kettle corn, so that tells me about the input. We're talking about the cost and its rate of change. So cost is increasing. That's because we're talking about c prime. We're talking about its rate of change. So c prime is a rate of change in costs. This number is bigger than 0. It's a positive number. So if you have a rate of change that's positive, just like an upward sloping line, that means that cost itself is sloped upward there. It's growing. And then we actually we make a statement about the number itself. So cost is increasing at a rate of $0.3 per additional quart produced. Now, the units on this we figure out are exactly the same as slope. They're the units of output, dollars, divided by the unit of input, quarts produced. So this is C divided by K, basically. And that will always be the case for our derivatives. We always take the units on output and divide by the units on input. So this statement encompasses all the numerical and mathematical things in this statement. It talks about the input, talks about the output, talks about the function that we're studying. So, I mean, that took about a whole minute just to describe its importance, but I hope I'm conveying that to you. We'll be back in the final video for this section with one more applied example of the derivative and a discussion of continuity.